Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the radius of this circle, and in the second question, we'll find out the area of this circle using two different methods. So let's start with the first question. In the drawing, we have a circle, and this is the right angle ABC. This is angle ABC, this is the right angle. This is side AB, this is equals to 4 units in step. This is line 7 AD, this is equals to 4 units in step. This is line 7 DC, this is equals to 1 unit in step. This is point O, that is the center of this circle. Again, our task is to find out the radius of this circle. So here we can implement rule 25. We can rule 25, according to rule 25, from a common start point, this is the common start point, point P. We will draw a tangent. We have tangent from the common start point, point P, we have tangent PA. That is tangent to this circle, point A. In addition, from the same common start point P, we have secant PC that cuts the circle 2 points, B and C. So in this drawing, the following equation is true that PA square equals to PB times PC. Again, PA square equals to PB times PC. So we can implement rule 25 in our drawing. Once good in our drawing, this is the common start point, point C. From this common start point, point C, we have tangent CE, that is tangent to this circle, point E. In addition, from the same common start point, point C, we have secant CA that cuts the circle 2 points, D and A. So all the requirements of rule 25 are satisfied, and therefore we can implement rule 25. So already done. If we focus on this common start point, point C, we have tangent CE, and from the same common start point, point C, we have secant CA that cuts the circle 2 points, D and A. So all the requirements of rule 25 are satisfied, and therefore we can implement rule 25. According to rule 25, the following equation is true, that CE square equals to CD times CA. CE square equals to CD times CA. Then again, according to rule 25, if we focus on the common start point, point C, the following equation is true. That CE square equals to CD times CA. CE is the missing side, so electricity, so it is CE square equals to CD. CD is 1 times CA. C in total equals to 1 plus 3, that is 4. So in total, we found out that CE square equals to 1 times 4. 1 times 4 is 4, so CE square equals to 4. Here we take a root out of this equation, and we get that CE, tangent CE equals to the square root of 4, that is 2. So the length of tangent CE is 2 units. CE equals to 2 units in its length. This is tangent CE, it equals to 2 units in its length. In the next step, we will implement the Pythagoras theorem on this big right triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I'll copy the right triangle ABC in a new page, and We will implement on it the Pythagoras theorem. The hypotenuse AC equals to 1 plus 3, that is 4. AB equals to 3, and BC is the missing side. Here by PT is the formation for Pythagoras theorem. So finally, this is the right triangle ABC that is going from the original drawing. This right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So I write it down. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16. And it is equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9. Plus BC squared. BC is the missing side, so leave it as it is. So in total, if you found out that 16 equals to 9 plus BC squared. Here we subtract 9 from this equation, and we get that 16 minus 9 is 7. So 7 equals to BC squared. Here we take a root out of this equation, and finally we get that BC, the left of the missing side BC, is equal to the square root of 7 units. So here, this is the missing side BC, this is equal to the square root of 7 units in its length. What is the length of this missing line 7BE? From the drawing, it is very easy to see that BE in total equals to BC minus CC. B equals to BC minus CC. So write it down. BE equals to BC minus CC. So BE equals to BC. BC is equal to 7 minus EC. EC is 2. So in total, we found out that BE equals to the square root of 7 minus 2 units in its length. This is 7BE, that is equal to the square root of 7 minus 2 units in its length. It is given us the question that point O is the center of the circle. So we join points O and D together by a straight line. Point O is the center of the circle, point E is the point of the circle itself. Therefore, O is the radius of this circle. We define the radius of this circle as R, so O equals to R. So the radius OE is equals to R, the radius OE is drawn to point E, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will do another construction. That is to say, from this point O, that is the center of the circle, we will draw perpendicular on side AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular point O and AB. This point is point L. By doing this construction, we can do quadrangle LOEB. In quadrangle LOEB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its size. So in quadrangle LOEB we have 4 right angles, and therefore according to rule 5, quadrangle LOEB is a rectangle. So if you know, this is quadrangle LOEB, that is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LOEB, side OE must be equal to the opposite side LB, but OE is out, therefore the opposite side LB must be also equal to R units in its length. Likewise, according to the same rule, in the same rectangle LOEB, side EB must be equal to the opposite side OL, but EB is square root of 7 minus 2, therefore the opposite side OL must be equal to the square root of 7 minus 2 units in its length. What is the ref of this missing 9 segment AL? From the drawing it is very easy to see that AL in total equals to AB minus LB. Again, AB minus LB equals to AL. So I write down AL equals to AB minus LB. So AL equals to AB equals to 3 units in its length according to this equation, minus LB is R. So in total, we can find out that AL equals to 3 minus R units in its length. This is 970 AL, that is equals to 3 minus R units in its length. In the next step, we'll join points O and A together by a straight line. Point O is the center of this circle, point A is the point of the circle itself, therefore OA is the radius of this circle. This is equal to R according to our definition. In the next step, I'll copy the right triangle ALO, the right grand triangle ALO in the new page, and we will implement on this right grand triangle ALO the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right green triangle A and O that are coming from the original drawing. This right triangle A and O, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AL squared plus LO squared. So write it down. AO squared, the square of the hypotenuse, equals to AL squared plus LO squared. AO is R, therefore AO squared is R squared, and it is equals to AL squared. AL is 3 also. Therefore AL squared is 3 R squared plus LO squared. LO is square root of 7 minus 2, therefore LO squared is square root of 7 minus 2 squared. So in total we should find out that R squared equals to 3 minus R squared plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared. 3 minus R squared equals to 3 squared, that is 9, plus R squared, minus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared in total equals to 0.417. So in total we should find out that R squared equals to 9 plus R squared minus 6R plus 0.417. Here we have R squared on both sides of this equation, so R squared gets cancelled, R squared cancels R squared. In this side of the equation we left with nothing, that is to say 0. While on the other side of the equation we have 9 plus 0.417 is 9.417 on 6R. So in total we should find out that 0 equals to 9.417 on 6R. Here we add 6R to the equation, and finally we get that 6R equals to 9.417. Here we divide this equation by 6, and finally we get that R, that is the radius that you are looking for in this question, the radius of the second R equals to 9.417 over 6 is 1.57 units. So if you found out that the radius that you are looking for in this question, that is the radius of this circle, is equal to 1.57 units in its length. So we finish with the first question. In the next step I will present to you the second question, and we solve the second question in 2 different methods. Our task in the second question is to find out the area of this circle. Again, our task in the second question is to find out the area of this circle. So in the drawing we have a circle. This is line 7BC, this is equals to 6 units in its length. This is called VA, this is equals to 13 units in its length. This is line 7CD, this is equals to 18 units in its length. Those two angles are both right angles. Again, our task is to find out the area of this circle. So first of all, those two right angles are defined as one-sided interangles. The sum of those two one-sided interangles is equal to 180 degrees, and therefore, according to rule 27, if the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. So the sum of those two one-sided triangles is equal to 180 degrees, and therefore they are located between two parallel lines. That is to say, BA is parallel to CD. BA is parallel to CD according to Rule 27. So write it down. If you found out that chord BA is parallel to line 7 CD according to Rule 27. In the next step, we define the center of this circle. This point is point O, and from point O, that is the center of the circle, we will draw perpendicular on CB. From point O, that is the center of the circle, we will draw perpendicular on CD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and CD. This point is point M. In the next step, we will extend the perpendicular OM until it touches chord BA. Repeat again, we will extend the perpendicular OM by sideline until it touches chord BA. And we define the touching point of the extended perpendicular OM with chord BA. This point is point N. So we already found out that CD is parallel to BA, and therefore the perpendicular OM, or the extended perpendicular OM, must be also perpendicular to chord BA. Well, chord BA is parallel to CD. Therefore, the extended perpendicular OM must be also parallel to BA. So this angle equals to 90 degrees, and this angle equals to 90 degrees. I will explain again why those two angles are right angles. We know that CD is parallel to BA. So if we have two lines that are parallel to each other, for example, this is line A, this is line B, and we know that line A is parallel to line B. So from this point, we will do perpendicular on line A. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. If we extend the perpendicular CD by third line until it touches line B, then the extended perpendicular CD will be also perpendicular to line B. Why? Because line A is parallel to line B. Therefore, the extended perpendicular CD must be also parallel to line B. Why? Because they are parallel to each other. Again, the extended perpendicular CD must be also perpendicular to line B, because they are parallel to each other. Line A is parallel to line B. So here we have CD is parallel to BA, and therefore the perpendicular to CD, the extended perpendicular OM, must be also perpendicular to BA, because those two line segments are parallel to each other. So by doing this construction, you get the idea. For the other BCMN, inside quadrilateral BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees. According to the rule, that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral BCMN, we have 4 right angles, and therefore quadrilateral BCMN is a rectangle according to all 5. So write it down. And then BCMN is a rectangle because it has 4 right angles. ON is perpendicular to BA, so ON is a perpendicular, it is absolutely a straight line. So if you focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to all 3. All 3 state that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is the right angle according to our construction, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we will do another construction, that is to say from point A we will do perpendicular on CD. Again from point A we will do perpendicular on CD. So actually this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CD. This point is point L. By doing this construction, we created the lower quadrilateral MNLA. Inside the lower quadrilateral MNLA we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 missing angle, so that must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 missing angle must be equal to 90 degrees in its size. So in quadrilateral MNLA we have 4 right angles, and therefore according to rule 5, quadrilateral MNLA is a rectangle. In conclusion, we found out that both those two quadrilaterals are rectangles. So here we can implement rule 19. Repeat quickly rule 19 and we'll implement rule 19 in our drawing. According to rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. In the drawing we have a circle, point O is the center of the circle, AB is the chord in the circle. According to this rule, rule 19, the perpendicular OM, that is one from point O, that is the center of the circle, the perpendicular OM bisect chord AB. That is to say, the perpendicular OM divides chord AB into two halves. The first half is AM and the second half is MB, and of course AM equals to MB. So according to this rule 19, the perpendicular from the center of the circle towards any chord bisect the chord. We can definitely implement rule 19 in our drawing. Why? Because in our drawing, O is the center of the circle, so from point O, that is the center of the circle, we have perpendicular OM, we have perpendicular ON on chord BA. Again, from point O, that is the center of the circle, we have perpendicular ON on chord BA. And according to rule 19, perpendicular ON on chord BA bisects chord BA. BA in total equals to 13, so perpendicular OM divides chord BA into two halves. Each half must be equal to 13 over 2. So the first half BN is 13 over 2, that is 6.5. And the second half NA is also 13 over 2, that is 6.5. So in the upper rectangle BC and M, side VN is equal to the opposite side Cm, but Bn is 6.5, therefore the opposite side Cm must be also equal to 6.5 units in its length, according to the rule that the opposite sides of a rectangle are equal to each other. So side Cm must be also equal to 6.5 units in its length. Likewise, in the lower rectangle NMLA, side NA must be equal to the opposite side ML. But NM is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this? This is 97 LD. From the drawing it is very easy to see that LD in total equals to CD minus CL. Again, CD minus CL equals to LD. So write it down. We actually found out that the missing 97 LD is equal to CD minus CL. So LD equals to CD. CD is 18, according to what is called the question, minus CL. CL in total equals to 6.5 plus 6.5, that is 13. So in total, LD equals to 18 plus 14, that is 5. LD equals to 5 units in its length. This is the missing 97 LD, that is equals to 5 units in its length. In the next step, we'll extend 97 DC by straight line until it touches the circle. And when you find the touching point of the extended 97 DC with this circle, this point is point T. By doing this construction, we get it there, called TD. This is called TD. Now we can implement Rule 19 on chord TD. Why? Because from the center of this circle, that is to say from point O, we have perpendicular OM on chord TD. Again, from the center of the circle, that is to say from this point O, we have perpendicular OM on chord TD. And according to Rule 19, perpendicular OM bisect chord TD. If perpendicular OM bisect chord TD, it means that TM equals to MD. So at the moment, we found out that according to Rule 19, TM equals to MD. TM equals to MD according to Rule 19. But MD in total equals to 6.5 plus 5, that is 11.5. So we can write that MD equals to 11.5 units in its length. And from this equation, Tm equals to Md equals to 11.5, we will derive that Tm is also equals to 11.5 units in its length. This is 97 Tm, that is equals to 11.5 units in its length. From one side, Tm equals to 11.5. But from the other side, Tm is also equals to Tc plus Cm. So we can write that from the other side, Tm equals to Tc plus Cm. And from this equation, 11.5 equals to Tm equals to Tc plus Cm, we derive that 11.5 equals to Tc plus Cm. So 11.5 equals to TC plus CM, but CM equals to 6.5. CM equals to 6.5. So we solve CM by 6.5, and we get in total that 11.5 equals to TC plus 6.5. Here we subtract 6.5 from the equation, and we get that TC equals to 11.5 minus 6.5 is 5. So TC equals to 5 minutes in its length. This is 970 TC, this equals to 5 minutes in its length. In the next step, we'll extend 97 BC by straight line until it touches the circle. And we'll define the touching point of the extended 97 BC with this circle. This point is point Q. By doing this construction, we get here chord BQ. This is chord BQ that intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. So write it down. Chord BQ intersects with chord TD at point C. The intersection point occurs at point C. This point C. And whenever you have two chords that intersect with each other, you can implement rule 15. So repeat quickly rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So in the moment we have a circle, this is called AB that intersects with chord CD at point O. According to this rule 15, in this moment the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 15 in our drawing. Well, because in our drawing, we have chord BQ that intersects with chord TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement here rule 15. According to rule 15, the following equation is true, that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. So write it down. If you found out that TC times CD equals to BC times CQ. Repeat again, according to rule 15, the following equation is true. That TC times CD equals to BC times CQ. TC is 5 times CD. CD is 18, and it is equals to BC. BC is 6 times CQ. CQ is the missing side, so leave this it is. So in total, if you found out that five times 18 equals to 6 times CQ. Here we will divide this equation by 6, and we get that CQ the missing line segment CQ is equal to 18 over 6 is 3, and 3 times 5 is 15. So CQ equals to 15 units in its length. This is the missing line segment CQ. That is equals to 15 units in its length. If you read by extended line segment BC by straight line, we created here triangle QBA. Triangle QBA equals to 90 degrees in its size according to what is given as the question. So in the next step, we join points Q and A together by a straight line. We join points Q and A together by a straight line. So in the drawing we have, this is triangle QBA, this is equals to 90 degrees in size, and triangle QBA subset on code QA. Again, triangle QBA subset on code QA. So here we can implement rule 5. Repeat quickly rule 5. According to rule 5, any triangle that is equal to 90 degrees in its size must subset on the diameter of the circle. So in the drawing we have a circle. This is triangle MAN that is equal to 90 degrees in size, and therefore triangle MAN must subset on the diameter of the circle. And indeed triangle MAN subset on MN on code MN, that is the diameter of the circle. So according to this rule 5, any triangle that is equal to 90 degrees in size must subset on the diameter of the circle. You can definitely implement rule 5 in our drawing. Why? Because in our drawing we have triangle QBA that is equal to 90 degrees in size, and therefore according to rule 5, triangle QBA must subset on the diameter of the circle. Triangle QBA subset on code QA, and therefore according to rule 5, code QA must be the diameter of the circle. So write it down. If you found out that according to rule 5, code QA is the diameter of the circle. The diameter of any circle is twice as long as the radius. So if you define the radius of this circle as r, then the diameter of QA must be equal to 2r. So QA equals to 2r. So it is twice as long as the radius. This is the diameter of QA. It is equals to 2r. In the next step, I'll copy the big right triangle QBA in the new page and implement on this right big triangle QBA the Pythagoras theorem. This is side BQ, that is equals to 6 plus 15, that is 21. This is side BA, that is equals to 13 units in its length according to what is given as an equation, and the hypotenuse QA equals to 2r. This is also the diameter of the circle. Here by PT is the proportion for Pythagoras theorem. So actually, this is the right triangle QBA, that is copied from the original drawing. In this right triangle QBA, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. So I write it down. QA squared, that is the square of the hypotenuse, is equal to QB squared plus BA squared. QA is 2r, therefore QA squared is 2r squared, that is 4r squared, and it is equal to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441, plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total, if you want to know that 4r squared equals to 441 plus 169. So 4r squared equals to 441 plus 169 is 610. So in total, if you found out that 4r squared equals to 610, here we divide this equation by 4, and finally we get that r squared equals to 610 over 4. 610 over 4 is 152.5. In total, if you found out that r squared equals to 152.5. Our task is to find out the area of the circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. But again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. But we already found out that the radius of our circle squared is r squared. Therefore, the area of our circle must be equal to pi r squared. So it is pi times r squared, but r squared is 152.5. So we substitute r squared in this expression by 152.5 and get the area of this circle, that is the area that we are looking for this expression. It is equal to either 152.5 times pi square units in size in terms of numbers. It is equal to 479.09 square units in its size. Because again, we should find out that the area of this circle, that is the area that we are looking for this expression, it is equal to either 152.5 times pi square units in its size. So in terms of numbers, the area of this circle equals to 479.09 square units in its size. So we finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. In the second method, we'll use some of the things that we already found out in the first method. That is to say, in the first method, we already found out that this is line segment C cubed, that equals to 15 units in itself, and this is line segment C, that equals to 5 units in itself. So we use those two things that we already found out in the first method. So in the drawing, we have, this is chord BQ that intersects with chord TD at 90 degrees at point C. Again, in the drawing we have chord BQ that intersects with chord TD at 90 degrees at point C. The intersection point occurs at point C. Whenever we have two chords that intersect with each other at a right angle, like here, you can implement rule 26. So, repeat quickly rule 26. So it's rule 26. Rule 26 is true in any circle. So in any circle, if two chords A, chord AB and chord CD intersect with each other at a right angle, chord AB intersects with chord CD at 90 degrees. They create at the intersection point that is point O, 90 degrees with each other. So whenever your two chords intersect with each other at 90 degrees, you can implement rule 26. And according to rule 26, the following equation is true. It is following. That AO square plus OB square plus CO square plus OD square equals to 4R square. Again, according to rule 26, the following equation is true. That AO square plus OB square plus CO square plus OD square equals to 4R square. And R is the radius of this circle. So we can definitely implement rule 26 in our drawing, because in our drawing we have chord TD that intersects with chord PQ at 90 degrees at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement the rule 26. So write it down. If you found out that in our original drawing, chord TD intersects with chord BQ at 90 degrees. At the intersection point is point C. They create between them with each other 90 degrees. This is a right angle. In the intersection point occurs at point C. This is point C. Repeat again. Chord TD intersects with chord BQ at 90 degrees at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement rule 26 in our drawing. According to rule 26, the following equation is true: that TC square plus CD square plus BC square plus CQ square equals to 4R square. And R is the radius of this circle. Repeat again. According to rule 26, the following equation is true: that TC square plus CD square plus BC square plus CQ square equals to 4R square. TC is 5, therefore TC square is 5 squared, this is 25, plus CD square. CD is 18, therefore CD square is 18 squared, this is 324, plus BC square. BC is 6, therefore BC square is 6 squared, this is 36, plus CQ square. CQ is 15, therefore CQ square is 15 squared, this is 225, and it is equal to 4R square. So if you found out that 25 plus 324 plus 36 plus 225 equals to 4R square. 25 plus 225 is 250. And 324 plus 36 is 360. So in total, if you found out that 250 plus 360 equals to 4R square. 50 plus 360 is 610 equals to 4r squared. Here we divide this equation by 4 and finally get that r squared equals to 610 over 4 is 152.5. So if you found out that r squared equals to 152.5, our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Because again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. But the radius of our circle squared is r squared. So in total, the area of our circle must be equal to pi r squared. So it is pi times r squared, but r squared is 152.5, so we substitute r squared by 152.5. So in total, if you found out that the area that we are looking for this expression, that is the area of this circle, according to the second method, is equal to either 152.5 times pi squared units in size, or in terms of numbers, it is equal to 479.09 square units in its size. So, in both methods, we found out actually that the area of this circle equals to either 152.5 times pi square units in size, or in terms of numbers, the area of this circle equals to 479.09 square units in size. So we finish with the with the second method and the second question. In the next step, I will summarize the lecture. We start with the first question, of course. In the first question, our task is to find out the radius of this circle. So in that moment, we have a circle. This is the right angle ABC. Side AB equals to 4 units in its length. This is line segment AQ. This equals to 3 units in its length also. This is the short line segment DC. This is equals to 1 unit in its length. This is the angle ABC. This is the right angle. Again, our task is to find out the radius of this circle. So here we can implement rule 25. From the common standpoint point C we have tangent CE, and from the same common standpoint point C we have secant CA that cuts the circle to points D and A. So all the requirements for rule 25 are satisfied, and therefore we can implement here rule 25. According to rule 25, the following equation is true, that CE squared equals to CD times CA. Again, CE squared equals to CD times CA. And again, according to rule 25, the following equation is true, that CE squared equals to CD times CA. CE is the missing side, so leave it as it is, and it is equals to CD. CD is 1, and CA in total equals to 1 plus 3, that is 4. So CE squared equals to CD, that is 1, times CA, that is 4. So CE squared equals to 1 times 4, that is 4. CE squared equals to 4. Here we took all the out of this equation and found out that CE equals to the square root of 4, that is 2. This is tangent CE, that is equals to 2 units in its length. In the next step, we implemented the Pythagoras theorem on this right big triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle ABC, that the point of the original domain. AC, the hypotenuse AC total equals to 1 plus 3, that is 4, and AB equals to 3. BC is the missing side. So in this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16. plus AB square. AB is 3, therefore AB square is 3 squared, that is 9, plus BC square. BC is the missing side, so it is. So in total, we should found on the 16 equals to 9 plus BC square. Here we subtracted 9 from this equation, and we found out that 16 minus 9 is 7, so 7 equals to BC square. Here we took out of this equation, and we found out that BC equals to the square root of 7 units in its length. Okay. This is side BC, this equals to the square root of 7 units in its length. What is the length of this missing line 7? BE. BE equals to BC minus EC. And again, B equals to BC minus EC. So B equals to BC, that is square root of 7, minus EC, that is 2. So in total, B equals to the square root of 7 minus 2 units in its length. This gives us the equation that point O is the center of the circle. So from point O, we join points O and D together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OE is the radius of this circle. We define the radius of this circle itself, so OE equals to R. The radius of OE is equals to R, the radius of OE is drawn to point A, that is the point of tendency BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. The next step, we did another construction, that is to say from point O, we draw perpendicular on AB. Again, from point O, we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point O and AB, this point is point L. We're doing this construction, we can do quadrilateral OLBE. Inside quadrilateral OLBE, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this 450 again, so that must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. The top of this 450 again must be equal to 90 degrees in its size. So in quadrilateral OLBE, we have 4 angles. And according to rule 5, any quadrilateral that does 4 angles must be this rectangle plus the square. So in relation to quadrilateral OLBE is rectangle because it has 4 rectangles. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle OLBE, side OE must be equal to the opposite side LB. But OE is out, therefore the opposite side LB must be also equal to R units in its length. Likewise, according to the symbol rectangle LOEB, side BE must be equal to the opposite side LO. But BE is square root of 7 minus 2, therefore the opposite side LO must be also equal to the square root of 7 minus 2 units in its length. What is the length of this missing line 70 AL? AL equals to AB minus LB. And again, AL equals to AB minus LB. So AL equals to AB, that is 3, minus LB, that is R. So in total, AL equals to 3 minus R. In the next step, we join points O and A together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the circle, that is equal to R. In the next step, I copied the right hand triangle AOL ALO in a new page and implemented the Pythagoras theorem on this right hand triangle ALO. This is the right hand triangle ALO that is coming from the original drawing. In this right triangle ALO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AL squared plus LO squared. AO is out, therefore AO squared is R squared, and it is equals to AL squared. AL is 3 minus R, therefore AL squared is 3 minus R squared, plus LO squared. LO is square root of 7 minus 2, therefore LO squared is square root of 7 minus 2 squared. So in total we should find out that R squared equals to 3 minus R squared, plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared equals to 3 squared, that is 9, plus R squared minus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared in total equals to 0.417. So in total we should find out that R squared equals to 9 plus R squared minus 6R plus 0.417. Here we have R squared on both sides of this equation. So R squared will get cancelled, so cancel R squared on this side of the equation we left in flapping, that is to say 0, and on the other side of the equation we have 9 plus 0.47, that is 9.417 minus 6R. So in total, if you found out that 0 equals to 9.417, now 6R. Here we added 6R to this equation. If I found out that 6R equals to 9.417, here we divided this equation by 6, and if I found out that R, that is the other that we're looking for in this equation, it is equal to 9.417 over 6, that is 1.57 units. So if you found out that the radius R of this circle is equal to 1.57 units in its length. So we finish with the first question. In the next step I present to you the second question, and we solve the second question in two different methods. In the second question, our task is to find out the area of this circle. So in the drawing, we have a circle. This is diameter BC. This is equal to 6 units in its length. This is called B8. This is equal to 13 units in its length. This is 97 CD. This is equal to 18 units in its length. Those two angles are both right angles. Again, our task is to find out the area of this circle. So first of all, those two angles, those two right angles are defined as one-sided interangles. And according to rule 7, if the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. The sum of those two right angles is of course equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, BA is parallel to CD. And again, BA is parallel to CD according to rule 27. In the next step, we define the center of this angle. This point is point O. And point O, we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and CD. This point is point N. In the next step, we extended the perpendicular OM by side line until it touches point BA. We define the touching point of the perpendicular OM with the extended perpendicular OM with code BA. This point is point N. So here, because of the fact that BA is parallel to CD, it means that the perpendicular OM, or the extended perpendicular OM on CD, must be also perpendicular to chord BA. Why? Because if you have two lines that are parallel to each other, here line A is parallel to line B, then the perpendicular to line A, the extended perpendicular to line A, must be also perpendicular to line B. Why? Because they are parallel to each other. Therefore, the extended perpendicular OM to CD must be also perpendicular to chord BA. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to what I've already explained to you. So by doing this construction, we can do the quadrilateral BCMN. Inside quadrilateral BCMN, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this 4 preceding angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 preceding angle must be equal to 90 degrees in its size. So inside quadrilateral BCMN, we have 4 right angles, and therefore, according to rule 5, quadrilateral BCMN is a rectangle, because it has 4 right angles. ON is a perpendicular, it is absolutely a straight line. So if you focus on the lower side of the straight line ON at point N, if the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is the right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did another construction, that is to say, from point A, we do perpendicular on CD. Again, from point A, we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CD. This point is point A. By doing this construction, we can do the lower quadrangle MN-AL. Inside the lower quadrangle MN-AL, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total the mass is equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in size. So inside quadrangle MNLA we have 4 rectangles, and therefore according to rule 5, quadrangle MNLA is a rectangle. Now we can implement rule 19 in our drawing. According to rule 19, if from the center of the circle you will draw perpendicular towards any chord, it will bisect the chord. From the center of the circle that is to say from point O, we have perpendicular ON on chord BA. And therefore according to rule 19, perpendicular OM on chord BA bisect chord BA. PA in total is 13, therefore each half must be equal to 13 over 2, that is 6.5. So the first half BAN is 6.5, the second half NA is also 6.5. So in rectangle BCMN, the opposite sides are equal to each other. That is to say, side BN is equal to the opposite side CM, but BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. Likewise, in the lower rectangle MNLA, side NA must be equal to the opposite side ML, but NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this missing element LD? LD equals to CD minus CL. Again, LD equals to CD minus CL. So LD equals to CD, that is 18, minus CL, that is 6.5 plus 6.5, that is 13. So in total, LD equals to 18 minus 14, that is 5. LD equals to 5 units in its length. In the next step, we extended 97 DC by sideline until it touches the circle. We define the touching point of the extended 97 DC with this circle. This point is point T. By doing this construction, we can do code TD. This is code TD. Here we can implement all 19 in code TD because we have from the center of this circle, that is to say from point O, we have perpendicular OM on chord TD. According to rule 19, perpendicular OM on chord TD bisect chord TD. That is to say TM equals to MD. And again, according to rule 19, TM equals to MD. But MD in total equals to 6.5 plus 5, that is 11.5. So we can write here that MD equals to 11.5, and from this equation TM equals to MD equals to 11.5. We will derive that Tm is also equals to 11.5 units in Tm equals to also 11.5 units in its length. So from one side Tm equals to 11.5, but from the other side Tm is also equals to Tc plus Cm. So from the other side Tm is also equals to Tc plus Cm. And from this equation 11.5 equals to Tm equals to Tc plus Cm. We will derive that 11.5 equals to Tc plus Cm. So 11.5 equals to Tc plus Cm. Tc is the missing side, so it is plus Cm. Cm equals to 6.5, so we substitute Cm as 6.5. So in total, if you found out that 11.5 equals to Tc plus 6.5. Here we subtract the 6.5 from this equation, and we found out that the missing 97 Tc is equals to 11.5 minus 6.5 is 5. So this is the missing 97 Tc is equals to 5 units in its length. In the next step, we extended 97 BC by sideline until it touches the circle. We define the touching point of the extended 97 BC with this circle. This point is point Q. By doing this construction, we get a chord BQ that intersects with chord TD at point C. Again, we have chord BQ that intersects with chord TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement here rule 15. According to rule 15, the following equation is true that Tc times Cd equals to Bc times Cq. Again, Tc times Cd equals to Bc times Cq. And again, according to rule 15, the following equation is true that Tc times Cd equals to Bc times Cq. Tc is 5, Cd is 18, Bc is 6, and Cq is the missing side. So according to rule 15, if you found out that 5 times 18 equals to 6 times Cq. Here we divided this equation by 6 and found out that Cq equals to 18 over 6 is 3, and 3 times 5 is 15. So Cq equals to 15 units in its length. So in the drawing we have, this is perpendicular QBA, this is equals to 90 degrees in size. So in the next step, we join points Q and A together by side line. So perpendicular QBA is equals to 90 degrees in size, subtend on chord QA. Again, perpendicular angle QBA, that is the right angle, subtend on chord QA. And according to rule 5, any perpendicular that is equals to 90 degrees in size, like this perpendicular QBA, must subtend on the diameter of the circle. Perpendicular QBA, that is the right angle, subtend on QA, and therefore according to rule 5, QA must be the diameter of the circle. Again, QA is the diameter of the circle according to rule 5. The diameter of any circle is twice as long as the radius. So if the radius is out, then the diameter QA must be equal to 2r. So QA equals to 2r, BQ equals to 6 plus 15, that is 21, and BA equals to 13. So in the next step, I copied the right triangle QBA in the page and implemented the Pythagoras form on this big right triangle QBA. So this is a big right triangle QBA, that is according to the original drawing. In this big right triangle QBA, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2r, therefore QA squared is 2r squared, that is 4r squared, and it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441, plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total, we found out that 4r squared equals to 441 plus 169. 441 plus 169 is 610. So in total, we found out that 4r squared equals to 610. Here we divided this equation by 4, and we found out that r squared equals to 610 over 4. 610 over 4 is 152.5. So in total, we found out that r squared equals to 152.5. Our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared, so in total the area of our circle must be equal to pi r squared. But r squared is 152.5, so we substitute r squared by 152.5, and finally found out that the area of our circle, it is equal to either 152.5 times pi square units in size. So in terms of numbers, the area of this circle equals to 479.09 square units in size. So we finish with the first method. In the next step, I present to you how to find out the area of this circle according to the second method. In the second method, we used with the fix that we have already found out in the first method. That is to say, we only found out in the first method that TC equals to 5 and CQ equals to 15, so we use those two fixes in the second method. In the second method, we used rule 26. We have here chord BQ that intercepts with chord TD at 90 degrees at point C. And whenever you have two chords that intercept with each other at 90 degrees, you can implement rule 26. And according to rule 26, quickly on rule 26. Rule 26 is for in any circle. So in any circle, two chords A, B, and CD intersect with each other at a right angle. At their intersection point, that is point O, they create between them 90 degrees. So they intersect with each other at a right angle. Then, in this moment, the following equation is true that AO square plus OB square plus CO square plus OD square equals to 4R square, and R is the radius of the circle. Again, whenever you have two chords that intersect with each other at a right angle, you can implement this rule. And in our drawing, we have chord TD that intersects with chord BQ at 90 degrees at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement rule 26. According to rule 26, the following equation is true that TC square plus CD square plus BC square plus CQ square equals to 4R square, and R is the radius of this circle. Then again, chord TD intersects with chord BQ at point 90 degrees at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement rule 26. According to rule 26, the following equation is true that TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. TC is 5, therefore TC squared is 5 squared, that is 25. CD is 18, therefore CD squared is 18 squared, that is 324, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 26. Plus CQ squared. CQ is 15, therefore CQ squared is 15 squared, that is 225. And this equals to 4R squared. 25 plus 225 is 250. 324 plus 36 is 360. So in total we found out that 250 plus 360 equals to 4R squared. 250 plus 360 is 610, so 610 equals to 4R squared. Here we divided this equation by 4, and we found out that R squared equals to 610 over 4 is 152.5. Our task is to find out the area of this circle. I'm sure you know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. But the radius of our circle squared is R squared, so the area of our circle must be equal to pi R squared. But R squared is 152.5. So we substitute R squared by 152.5, and in total we found out in both methods that the area of this circle, that is the area that we are looking for in this question, it is equal to either 152.5 times pi squared in size, in terms of numbers. The area of this circle equals to 479.09 square units in its size. Okay, thank you very much.